Yes. So you can do two complete rotations.
Two complete rotations.
Yes.
So this is a very fundamental property of the world that is somehow not discussed. I think I find it very interesting that people want to talk to me about the multiverse. Sometimes they want to talk to me about quantum measurement problems. But the idea that we are somehow based on a square root, and I would disagree with you slightly if you would permit it,
Go ahead.
that it's not just a question of the square root of the vectors. It's the square root of the algebra generated by the vectors that really the spinors are. This exterior or Clifford algebra.
Oh, yes.
This object has fascinated me my entire life, and it's very strange that all of the stability of matter and matter's strange properties with electron shells are all coming out of this weird knot that it appears everywhere in the universe, and it's not universally known that it's even there.
Yes, well, it's the difference between the fermions and the bosons. So the particles which have a spin which is half an odd number,
Right.
which have this curious property that you rotate them and they get back to minus themselves. And it's crucial for matter because the Pauli exclusion principle depends on the Fermi statistics, which is to do with this property.
So without this knottedness and the scissor trick or whatever you want to call it, we wouldn't have a periodic table and chemical elements.
You wouldn't have anything.
We wouldn't have anything.
Yeah, you wouldn't have it. You wouldn't have fermions. In other words, you wouldn't have things which have an exclusion principle. So, and the bosons, which are the opposite, they like to be on. If you have two bosons, you can have them in the same state. They rather like to be in the same state. So you get these things called Bose-Einstein condensates, where if you get them very cold, they all flop together into the same state. But for the fermions, it's completely the opposite. They hate to be in the same state, or they can't be. And this is what sort of pushes them apart. So you get the Fermi principle.
So you have this strange thing called the spin statistics theorem.
Yes.
That says that if things have a knottedness of a particular kind, then they either are highly individualistic or highly communistic, whatever you want to call it. Yeah. My question would be, there's another aspect of that I've been very curious about, which is when we have to treat these objects quantum mechanically, and you've, of course, thought a great deal about quantum theory, we have two totally different prescriptions for how to make these different objects quantum mechanical. But there's a one-to-one correspondence between these two utterly different treatments that matter and force get quantum mechanically. It's the darndest thing.
Yeah. When you get these two kinds of particle or two kinds of atoms, the bosons and the fermions. And it has to do with make a complete rotation. Do they come back to themselves or do they come back to minus themselves?
That's the topological bit.
Yeah.
But then there's this whole thing that might go under, like Berezin integration, which is no integration at all. I mean, you're effectively almost lying about what you're doing to the fermions to make them look like bosons. Yeah. And yet, what we seem to get out of this is that nobody, I don't think anyone could have anticipated that there would be a dictionary of two totally different structures, which seems to be almost word for word.
Yes, because they're not totally different in the sense that you take two fermion system and you get a boson. So they
have
all
to
part of the
be
same
related.
world. Yes, that's right.